Yeah, okay, so if we bump up to a triple integral, let me just write one here out. All right, 0 to 2, 0 to 3, 0 to 1. And kind of easy on ourselves. X, Y, Z, D, Z, D, Y, D, X. Well, once you get it, if you will, set up, like we have it here, and especially if the limits are just numbers, it's actually a fairly easy calculations. I mean, it's just kind of longer because you got 3 integrals to go through, but much the same as with the double integrals. Do the innermost first, so we're going to do our z's first, integrate with respect to z first. So it'll be 0 to 2, 0 to 3. So I'm integrating this with respect to z, the x and the y hold fixed. So the antiderivative would just be xy times 1/2 z squared, right? And do that from 0 to 1. And we'll do our y's and x's in that order next, right? So that would give me, so these I'm plugging in for, these are z's, right? So plug that in for z, what does that give us? xy times, well, it'd be 1/2 minus 0, right? Because plug in 1, you got 1. Plug in 0, you got 0. So it's just 1/2 xy. Well, guess what we do now? Now do the innermost that's left. So that would be integrating with respect to y. And I'm leaving off the limits. That, you know, probably not the most legal thing to do, but you can definitely go back and plug those in. I can save you a little bit, because these are kind of long. Anyway, so that's the, so I'm integrating with respect to y. So now I'd have the 1/2 x's. So that would be 1/2 x times just the antiderivative y. That's 1/2 y squared. And then that's, the y's go from 0 to 3. They'll still leave the x's to integrate with respect to. So what's that do? Well, now plug these in for y, so we'll have 1/2 x times 1/2 of 9. Half times 9. And then 0 gives me 0, so what is it, 9/4 x integral? That's all that's left. 1/2 times 1/2 times 9, 9/4. Easy enough, so that's 9/4 times 1/2 x squared. And that's going to go from, the x's go from 0 to 2 counter up there. So I got 9/8 times 4. And 0 to 0, so 9/2. So, yeah, it's not too terribly difficult process, especially, like I said, when we got the limits here. So, what we've done here is, yeah, it's the easiest, I guess you would say, of the triple integrals, because basically what I've done here is if I think about what my limits were, so the z's go from 0 to 1. Didn't write it out, but the y's go from 0 to 3. And then the x's go from 0 to 2. Well, if you think about that, what that basically gives you is a box. This is a box in 3 dimensions. Kind of be that first octant sort of box. I don't think we necessarily have to, but are you with me there? That if we just graph those out, that would just be a box. So when we go to triple integrals, the most basic thing we integrate over is this box, and sometimes in general they'll, I guess they use B for boxes. I'll call it box there. Now the other thing on the triple integral here is notice that what we're integrating over, triple integrating here is a function of three variables, x, y, and z. In general, you know, when we did the double integrals over d or whatever, f of x, y, we wrote dA here because we're integrating over this area D, but it's a two-dimensional area we're integrating over. And this was a three-dimensional graph. Of course, this, if we graph this, you're graphing in 4 dimensions, so I don't want to think probably too hard on that right now. But anyway, so in double integrals, we're integrating over an area. Well, when we go to triple integrals, we're integrating over a volume. And so that's what we're saying. We're talking about a box, three-dimensional. I don't know if that's exactly accurate for that particular case, but in this case, we're integrating over this box. So hence, we call it dV. Now, a couple other things to make note of. All right, so we went in this order in that particular case. Can we do it in a different order? Oh yeah. Actually, there's 6 different orders we could do for the order of our integrations. You know, we could switch out the x's and y's here. So dz, dx, dy. We could do y's first, and then x's, then z's, or y's, then z's, then x's, or x's first. You know, so there's 6 different possibilities there. So, you know, in 2 dimensions, you only have 2 options. Well, you got 6 different options there. So, yeah, it it gets complicated, as we said. All right, now, so that's integrating over a box. Well, that won't always be the case. So let's talk about, for a more general region, call it E. I think that's kind of what we did. And we did D, and we did D for that one. Okay, so yeah, what if we're not just integrating over a box, a more general region? Several possibilities would emerge there. We'll stick to, I think, mainly anyway, we're going to stick to what's called the type 1 region. That is, E is a region between the graphs of 2 continuous functions of x and y. In other words, 2 z equals graphs, okay? Z equals f1 of xy, z, so that's z1, z2 equals f2 of x comma y, in other words. See that? So E is going to be the region between those graphs. So we're still talking about a volume, but it's between two z equals graphs. And so, you know, shapes of that are endless, I guess you might say, because yeah, those three-dimensional graphs, they can get real complicated. But so just kind of they call them not F, but U's. I use their notation, so makes kind of sense. All right, so here's what we're going to do. All right, so just to kind of give you a general, try to draw this out. So XY plane wise, we're still talking about, so let me work our way through it. So E is going to be the XYZs such that, all right, so X comma Y is still, that's still going to be some area in the XY plane. So we're still talking about that sort of thing. So we still have that kind of two-dimensional, draw it kind of like my paper if I can. So D, I'm still talking about some, and I did a first quadrant one so we could. So we are still dealing with that. However, now instead of projecting it to one graph, if you will, we're projecting it to two z equals graphs. So here's what I did. All right, so we've got this, you know, this z equals graph for this u. Let's do u2 here. That'll be our top one. So you got this three-dimensional graph here. I'll do the and so that, you know, I messed up because that needs to be projected this over. All right, so that projects up to that particular surface, whatever it looks like. Oops. Just pay attention where my limits are there. All right, so you're projecting that. So that's that surface, but we're only taking that part that's covered or projected up from that D surface, or D in the XY plane, that D area. But then you've got this other one. So try to make it, well, it's hard to kind of make it different, but it's going to have some other, you know, undulations or whatever you want to call it there. So this other surface, call it, that's Z2, this is Z1, and U1, X comma Y. So you got this other surface, which, you know, it has more different bumps probably than your other surface. And so we're integrating over, instead of a box, we're integrating over this volume right here. It's complicated, for sure. Definitely a complicated deal. But just to kind of give you an idea of what we're dealing with. So yeah, so then your Z's range from U1 XY to U2 XY. And so hopefully, obviously there, we're going to first want to integrate with respect to Z, because Z is in terms of X and Y. Now, the other, well, that'll probably depend on what you got for D. It may make sense to do the Y's first. It may make sense to do the X's first. So that'll tell you the order we're going to go there. So here's kind of what it looks like. Well, but yeah, definitely, like I said, if we've got this type 1, what we can definitely say is because z depends on x's and y's, we're going to want to do that first, the z's first. So go from u1 of xy to u2 of xy. Z's first. And then you can decide on the double integral that's left whether you want to do the x's first or the y's first. Like I said, it'll probably depend on what d really looks like there. So, yeah, let's take a look at a couple of those here and then see what happens. First one I think is pretty well specified out for us, so I guess they'll do that some times. All right, so integral, triple integral over e, 6xy dv, where e is, I like this set notation here, x, y, z, our y's are between 0 and 2. The x's, they're between 0 and y minus 1. And then the z's are between 0 and y minus x. Like I said, this one's kind of specified out for us. You just have to, again, kind of interpret what is we've got. So, yeah, notice the z, well, one end anyway, the upper limit here, the z is depending on y and x. And so that tells me I better do z's first. So I'm going to do z's first. So z goes from 0 to y minus x. Right? Now, looking at the other two things here, what do you think we should do after z's? Because the x's are in terms of y here, that's what we're going to do next. The x is written, all of that, like the lower limit 0, but looking at that upper limit, yeah, the x is given as a function of y there, and so do those next. So 0 to y minus 1, and then do the y's 0 to 2. Okay? Make sense? So yeah, so now, yeah, we've got a triple integral, but the upper limits, well, we got some, they're not constant, just numbers, so a little bit more complicated. Doesn't take much to get it. It's not too bad, it's just, most of the ones we do are just kind of lengthy, so let's work our way through it. So yeah, you do the z's first, so 0 to 2, 0 to y minus 1. All right, so we're doing z's first. There's not a z here, so just treat the x and the y as constants. So the antiderivative would just be 6xyz, and then we plug in z to be 0 and y minus x. Oh, and yeah, I might leave off some limits here as we go along. So, okay, so again, these are z's. So plug those in for z. So I have 6xy times y minus x. And then, yeah, the lower limit 0. So 6xy times 0 is 0. Then I'm going to do the x's and the y's. So, yeah, probably the best thing to do here, because that's 0, go ahead and multiply, distribute that in, and then do the antiderivative. So that'd be what? 6xy squared minus 6x squared y. Now I'm going to do the x's. So the antiderivative, well, it's pretty nice one as far as antiderivatives go. Some of the others we come across with, but yeah, we're doing the x's, so the y's treat fixed constants. So it'll just be 1/2 x squared, half of 6. So it's going to be 3x squared y squared minus this, the antiderivative would be 1/3 x cubed. So 6 times 1/3 would be 2x cubed y. And then we're going to plug in, so the x's go back here. These are my x's. 0 to y minus 1. I like the 0 there. Then we'll do the y's next. Yeah, so these are x's. So plug those in for x's. So it'll be 3 times y minus 1 squared times y squared minus 2 times y minus 1 cubed times y. And the good news is 0, so just have to deal with that. Probably, yeah, doing some squaring and cubing. This squared be y squared minus 2y plus 1, then times y squared. So we're going to be doing 3y squared minus 6y. Whoops, multiply it all. So 3 times it, and then y squared times it would be 3y to the 4th minus 6y cubed, and then 3y squared. Then this, okay, y minus 1 cubed, cube it out, yeah, you get y cubed, I believe it's y cubed minus y squared plus y minus 1, 3. 3y squared minus 3y, or plus 3y. Get it right yet. Those are zeros. Yeah, just have to keep that out because you got to distribute the y. So multiply the -2 and the y in, so that'd be -2y to the 4th plus 6y cubed minus 6y squared, and then plus 2y. And luckily, yeah, there's some like terms, y to the 4th. Oh, let's cancel that. So plus minus 3y squared, because the 6y cubes cancel. And then 2y. And so, last but not least, all we have to do is the last integration, except they're not too hard, they're just long. 1/5 y to the 5th, antiderivative, oh, that's nice, minus y cubed, 3's are going to cancel. And then, oh, 2's cancel, so that's y squared, so that. And the y's were 0 to 2. So you got 1/5 times 2 to the 5th is 32, so 32 fifths minus 8 plus 4. And that, I believe, is 12 fifths. Not too bad, huh? A little bit longer, not too bad. All right. I'll give you one more here if there's no question. Look okay? All right. How about triple integral over E, where E is the solid tetrahedron bounded by two x plus 3y plus z equals 6, x equals 0, y equals 0, and z equals 0. So basically, these three means we're just limiting it to the that first octet. Three-dimensional quadrant 1. Yes. That's what that means. All right, now this, what's this? Just a plane. So you can actually probably draw this one out. If you go by intercepts, you got the x-intercept's 3, y-intercept's 2, and then the z-intercept is 6. Yeah, so that sets up a solid tetrahedron right there, because we're bounded by all the x equals 0, y equals 0, z equals 0's planes. So yeah, we're just talking about that. Pyramid-y looking shape there. All right. Well, I left off most of my triple integral. It's 2x dv. Get too excited, there it is. So I'm going to evaluate over 2x dv over that solid tetrahedron there. So how do I do it? Well, type 1 is the one we're focusing on here. So in type 1, we start with the z's, and so what would my z's go from? Well, you know, it's bounded by this z equals 0 plane, so it goes from z equals 0 up to the that plane right there. So I probably want to represent this as a z equals function here. So you're with me there. Z goes between 0 and that. 6 minus 2x minus 3y. Okay. All right, so that's my start of it anyway. The z's go from 0 to 6 minus 2x minus 3y. Z's first. Now, x's and y's next. Well, probably a good idea to look at what in the xy plane your area looks like. These type 1s anyway. Well, in the xy plane, easy enough to draw. You got a x is 3, y is 2, so we're just talking about that triangle right there, right? So do you want to do x's first or y's first? It doesn't matter. If we do the y's first, we're going from y equals 0 up to that line, so I can figure out that line. And there's a couple ways to do it. You know, use your y equals mx plus b, but notice this. When I'm talking the xy plane, that's z equals 0, and this can help you for ones that aren't lines. It's z equals 0. So if I put z equals 0 here, I've got 2x plus 3y equals 6. So that gives you that line right there, you see. And if you solve for y, 6 minus 2x, so divide by 3, y equals 2 minus 2/3 x. And so that would be my y's, go from 0 up to the 2 minus 2/3. And then it's easy. X's then just go from 0 to 3. Cover that up. So we did the Y's and the X's. Okay? Can you see how that works? So that one, yeah, we had to set the whole thing up. So it's a little bit of a process now, but that's just the beginning of the process because now we got to do the triple integral. Any question though? Concern? And notice we would get the same line here because you got a y-intercept of 2, down 2, run 3, same thing. So 2 ways to do that one. But it can help for those that aren't maybe necessarily lines when you project them down to the XY plane. All right, so we do the z's first, and yeah, it looks already off the bat here. It looks fun. Is that upper limit there? Let's see what else. What all we get into here. 0 to 3. I'll leave those off. Come back to those later. All right, then. So I'm doing the integral with respect to z. So it's just 2xz, isn't it? Z 0 to 6 minus 2x minus 3y. So that goes in for z. So we have the double 2x, 6 minus 2x minus 3y. So that gives me, what, 12x minus 4x squared minus 6xy. So now I'm doing an integral with respect to y. So that's not too bad. The x's are constant, so that'll just be 12xy minus 4x squared y minus, all right, so this one's got a y, so it'll be a half of y squared, but the half times the 6 will give me 3xy squared. That sound right? Believe that? Okay, and that's limits for the y. That was the second one, so it'll be 0 to 2 minus 2/3 x. Still have the x's to do. So these are y's here. So that'll be 12x times 2 minus 2/3 x minus 4x squared times 2 minus 2/3 x. Those aren't bad, but then you have 3x times 2 minus 2/3 x squared. Not too bad, but let's have to work our way out here. All right, so distribute the 12, it'll be 24. 12 times 2/3 minus 8x, here's what that would be. Distribute the 4x squared here, it'll be minus 8x squared plus 8/3 x cubed. Here we just have a little matter, we got to square that out, so it'll be 4 minus 4/3 minus 4 would be minus 8/3 x, and then minus 2/3 x times minus 2/3 x plus 4/9 x squared. Then we have the minus 3x times that, so it'll be minus 12x plus, ooh, 3's canceled, it'll be plus 8x, and then minus 3x times 4/9, it'll be minus 12/9 x cubed, ooh, that's x squared, plus 8x squared there, minus 12/9, but that'll 4/3 x cubed. So if we combine some like terms, oh, yeah, those will cancel. For x cubed, I've got 8/3 x cubed minus 4/3 x cubed, that's positive 4/3 x cubed. Those x squareds canceled out. So I'm out of x squared, right? Which leaves me, oh, I see what I did wrong. This is 12x right here. So that'd be 24x minus 8x squared, yeah. I knew I had x squared left, so I worked this earlier. All right, that helps, especially when you're filming. All right, so that's 24x and minus 8x squared, so make that change there. Yeah, so I do have an 8x squared minus 8x squared left there. Those cancel out with that mistake. Then the x's, I've got 24x or minus 12x is plus 12x. I believe that's, stand out there. All right, so now I've got antiderivative of that, so it'll be 4/3, 1/4, x to the 4th, minus, that'll be 8/3, x cubed, and that would be 6x squared, and then evaluating the x's, we're going from 0 to 3. That's nice, that would be 1/3 times 81, 8/3 times 27, 6 times 9, 54. Sorry, the right side. Answer is not yet. Question or concern?